Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, in this video, we're going to talk about the fundamental concepts of the integral and derivation, and sometime we're going to see the limit. Why for to use it or to use them for practical examples. For example, the insulation that comes from the sun that hits a PV panel. So how to use the integral to estimate the energy uh, in watt hour from the sun that can hit a PV panel, or what is the concept behind that. But before we use the example or see the example in engineering equation solver software, we're gonna check out some fundamental concepts we have here. The concept of derivative is at the core of calculus and modern mathematics. The definition of the derivative can be approached in two different ways. One is geometrical, as a slope of a curve. So when I tell you a slope of a curve, this means the derivative or the rate of a change. And the other one is physical. Yes, the rate of change. So this is the physical. Geometrical is the slope of a curve. So if you have a curve and you get the slope of it at a specific point, this is the derivative, or the rate of a change of y respect to x. This is the derivative. So historically, there was and may be still is a fight between mathematicians which of the two illustrates the concept of derivative based and which one is more useful. So a fight between mathematicians which of the two illustrates the concept of the derivative based and which one is more useful. So we will not dwell on this and will introduce both concepts. Our emphasis will be on the use of derivative as a tool. So this also the main point from this video. So our emphasis will be on the use of the derivative as a tool. So the physical concept of the derivative, this approach used by Newton in the development of his classical mechanics. The main idea is the concept of velocity and speed. So indeed, assume that you're traveling from A to B. What is the average velocity during that trip? It is given by, so the average velocity is the distance from A to B divided by the time to get from A to B. This is the velocity. It's meter per second. Okay. So if we now assume that A and B are very close to each other, we get close to what's called instantaneous velocity. Suppose that you are in or at A and B is very, very close to B. So this is not the average velocity. It will not be average velocity. Why? Because the time to get from A to B will be very, very, very small. So of course, if A and B are close to each other, then the time it takes to travel from A to B will also be small. Indeed, assume that a time t equal A. We are at A, okay? And if the time elapsed to get to B is delta t, so then we will be at B when the time, just add the initial time plus the delta t and you will be at B. Okay, this makes sense. So so if delta s is the distance from A to B, so the average velocity it will be delta s divided by delta t. So the instantaneous velocity at A will be found when delta t gets smaller and smaller. So this is the instantaneous velocity. It will be the limit delta s divided by delta t, but when delta t is very, very small and is close to zero. It's a huge difference between the average velocity and instantaneous velocity. So if t describe the position at time t, then delta s, it will be when you traveled minus the initial position. Okay, so this is the final position at time a plus delta t. You have an initial time a, and then you add delta t, so you reach it to the second point minus the initial point. So this makes sense. So the instantaneous velocity at a, it will be limit delta t tends to 0, and here is delta s, just use this formula divided by delta t. Okay, so this is pretty amazing. So if you have just a parabolic motion, suppose that you're moving in a parabolic way, so ft is equal t squared. So the instantaneous velocity at t equal a is given by, you know, this law. Okay, so just limit delta t to 0, it will be a plus delta t square. Why? Because you will put a plus delta t at each t square, okay, minus a square. So put a here. So for the first time, put this here. It will be square. Delete t and put this. It will be square. Minus delete t and put a. It will be a square. Then divide by delta t. So after finishing this, it will be a plus delta t overall by square minus a square divided by delta t. So when we finish this, it will be 2a plus delta t. So now it is the time to use the limit. So when we put delta t equal to 0, this means that it will finally we will get to a. So we conclude that the instantaneous velocity at t equal a, it will be 2a. So as you can see, it will be 2a. So this is the instantaneous velocity and the average velocity. Again, this instantaneous velocity is when delta t approach from 0. It is very, very small. So delta s, and here delta t. Here is delta s, final position minus initial position, and we use the time to express that. So just get the limit and you will find yourself in the gets to this result. Okay, so this concept of velocity may be extended to find the rate of a change of any variable, the change of your of the distance to the time. You are at A and then you went to B in a specific period of time. Okay, so this is the change of the distance with respect to the time. So this is the rate of change. Okay, and the rate of change of the velocity with time is the acceleration. The car is accelerating. Okay, so this is the average rate is delta y by delta x, and here is the same way. Okay, so as before, the instantaneous rate of a change, when I tell you instantaneous, just get the limit, but here it's not to with respect to the time, it is with respect to x. So when delta x approaches from 0 is pretty small, it will be like this. Okay, so the instantaneous velocity at x equal a, it will be dy by dx at a. Okay, so this is here, for example, the geometric concept of the derivative. We have here function x from this graph. Recall the graph of a function is a set of points. Okay, no problem with this at all. To get the slope or fix a point on the graph, x naught and fx naught, if the graph is a geometric figure is nice, smooth around this point, it is natural to ask whether one can find the equation of the straight line touching touching the graph at that point. Such a straight line is called tangent line at the point in question. So the concept of tangent may be viewed in more general framework. So note that the tangent line may not exist. We will discuss this later on, okay? One way to find the tangent line is to consider points, this, for example, and where an x is very close to x node, then draw the straight line joining both, like that. So remember when I say instantaneous or very close or time approach from 0, we're talking about the limit, okay? And also the slope, it is the change in y divided by x, as we know. So their equation will be determined by finding their slope. Okay, no problem with that. The tangent itself will have a slope m, which is very close to mx when x itself is very close to x. No, this is the concept of the limit once again. Okay, so the slope here in this case, it will be the limit. It will be the limit. So the slope is equal to the limit. So gentlemen, here is the slope is equal to the limit, and the rate of change, it means the derivative. And you can get, of course, the equation of the straight line by knowing a point and the slope of it. To know, get the slope, you have to get the limit. So this makes sense, okay? So as you can see, here is m equal f x node, and the writing m for the slope of the tangent line does not carry enough information. We want to keep track on the function fx at the point x node in our notation. So the common notation used is m equal fx node. And of course this is not correct because this is not fx node, it is f dash x node, but you do not see it. Yeah, this is dash because it is the derivative. Okay, so the derivative, I can get the derivative also from limit x to x naught fx minus fx naught divided by x naught minus x naught. Okay, so one last remark, sometimes it is more convenient to compute limits when the variable approaches 0. One way to do that is to make the translation along x-axis. You know this, we got it from the school classes. Okay, this is pretty easy. I just wanted to refresh your mind and our basics, then we can continue this video. So I do not see that this is complex. So again, just to sum up, the derivative is the slope of a curve at a specific point on it. Okay, and also it is the rate of a change. Why? Because I go from A to B in a specific period of time. So this is the change of the distance with respect to the time. So this is the velocity. But if A is very close to B, I will take no time. I came here just in 0 time. Okay, this is the practical concept. So instantaneous velocity, it will replace the average velocity, and when I talk about instantaneous, I will use the limit because I will use delta t approach from 0. Instantaneous, and we have here just use any equation you want, and then you use the just substitution. And here is the average rate and instantaneous velocity, and here is the slope of this curve at this point. And then we came to the slope, and the slope is the limit, and as you can see, okay, and it's also the rate of a change because I wanna see the rate of a change, okay, of the this with respect to the another variable. Okay, So now the integral is the area under the curve. So formulating the area under the curve is the first step toward developing the concept of integral. The area under the curve formed by plotting function f(x) as a function of x can be approximated by drawing rectangles of finite width and height f equal to the value of the function at the center of the interval. Okay, so we wanna get the area under the curve by calculating the area of each rectangle and then add uh, plus plus, and then we get the total area. And we have here the when the approximation to the area under the curve can be made better by making approximating rectangles narrower. So the idea of the integral is to increase the number of rectangles the end toward infinite by taking infinity by taking the limit as the rectangle width approaches zero. Again, when something approaches zero in instantaneous, we take the limit. Okay. So you know this the area under this line from 0 to xm is this from here to here multiplied by this. Okay, this is the area of the square or the rectangle, and here's the area of the triangle. And also, if we use more rectangles, it will give more accurate calculations. Okay, so you have to know exactly what's going on under the curve, how to optimize the integration method. If you use 1, 2, 3, 4, just 4 rectangles, no, it's better to use more rectangles. Okay, just to accurately get the area. So now, gentlemen, using engineering equation solver, here is the area under the curve is the integral of function y, which depends on x. So x is the variable we're gonna vary x varies, okay, and from 0 to 1. So let's see. So this is the area under the curve, so the integration or the integral from 0 to 1 for y, which is function of x. So when you calculate this, so the area under the curve is half. So this is the fastest way. Okay. So now I'm gonna prove it. How? Simply by, if you have no idea about the integration, just make a schedule or parametric table. Here is x and here is y, and from 0 must be the same or as the same as the integral limits, and then I will go and solve this table. So when x equals 0, y it will be 0, x it will have the same value. So when I plot it, okay, so be careful. Here is 0 and here is 0. Okay, so this is the area under the curve, or this line. It will be the area of the triangle. It will be half multiplied by 1 meter multiplied by 1 meter. So half multiplied 1 and 1, it will give you half. Okay, exactly like what we have just seen. It matches the area under the curve by the integral. So what I wanna tell you today from this video is no need to plot everything. It will take some time. It may not be accurate. As you can see, we have to make some approaches. If we have a curve like this, here we got a match because the geometry is quite simple. Okay, but when we use a curve, No need to make these kind of rectangles and then get the area of each one of them. No, just use the integral. We're gonna use this method next couple minutes or later. So what we got here also, this is the change x, and here is y. So now, so this is the integral. It means the area under the curve. Now let's come to the most amazing part, is the derivative. What is the derivative of this function? So f dash or y dash, it will be 1. It will be 1. Again, when I tell you about the derivative, this means the slope. This means the slope. So the slope and the derivative of this function is 1. This means, what does this mean? This means that delta y divided by delta x must be 1. Must be 1. So if you, for example, 0.2222 minus 0.1111, divide this value by the same, it will give you 1. So this is the slope and this is the derivative, and also it means the rate of change of y with respect to x. So we have here 3 amazing concepts. So now what happens if we make this? Now try to get the area. The area in no time or easily, I'm gonna get the integral, okay, of the same function for the same limits. I just added plus 1. I just added 1. Calculate it. The area, it is now 1.5. So we have 1 square meter plus half, okay? So why, if we do not have any idea about the integral, so just solve the table again, we'll find this. Okay, make a new plot. Okay, but here is a trick. Sorry, we have a problem. We have a problem here. So it must be 0, and here must be 0. Okay, and yeah, this is what I'm talking about. From 0 to 1, this is the integral limits, and here is the final. Make sure please that this is correct, and here is the limits match. Okay, so we have here, we started not from 0 like the previous plot, like this. We just started from here. So we added area to the original area. This is the original area. The area is half square meter. But now what we have just added is the area of this rectangle, or no, so this square, something like this, or something like that. So width and height, there's no problem. We have 1 meter and here 1 meter. Okay, so this is a square. So the area of this square is 1 square meter plus the area of this triangle. It is half multiplied by 1 meter multiplied by 2 minus 1, which is 1. So we have here half square meter plus 1. It will give you 1.5. Okay, remember the integral 1.5. So this is amazing. So what I'm telling you here is no need to make all these kind of things, just we want to get the integral by using the simple integral law. Okay, so we have just finished the integral part. Now we come to the funny part is y equal x plus 1. What is the derivative? The derivative is equal also 1. Oh my god, after adding 1, the slope and the derivative do not change, because we have just x. The derivative of x, it will be 1. And also this means that the slope is the same, 1.222 minus 1.111. So let's make it 1.111. It will be 0.111 divided by 4 twos minus 1111. It will be 0.999. Okay, so we have the same slope, 0.999. So this means that we do not have any change in the slope. This means also from this geometry that the slope of y equal x, it is equal to the slope of y equal x plus 1. Even if you put here 50, you will just increase the area. But the slope will be the same. So this is one of the most important points in this video. Increasing this number means that we will get a higher area. Okay, 550.11. Why? Because we're gonna increase the area under this line. But the slope is the same. To know this, you have to get delta y by delta x. And also from here, delta y from here to here divided by delta x. Okay. So for the conclusion now, if we change this, of course you will change everything. It is another story. It is another schedule table, and here comment, solve, plot, make a new plot. Well, as you can see here, it must be 0. So here is 0, and here is 2 3. Okay, this is 2 3. I know, to make it find that like that. Okay, so gentlemen, the area under this line is 1 multiplied by 1. It will be 1 square meter, and a half multiplied by 1 multiplied by 3 minus 1, which is 2. So we have here what? So we have here 2 square meter, and it matches. This is awesome. So also again the integral, just get the notepad. So the area, it will be x square, okay, divided by 2, so we're gonna cancel this, plus x, and from 0 to 1, this is the area or the integral or the integration of this function. It is 2x squared divided by 2. It will give you x squared plus x from 0 to 1. This means that we have 1 square, okay, plus 1, this, minus 0, okay, plus 0. This equal to 2. So we have here the integral is 2, and also the area under this line is 2. So this is pretty awesome. Okay. So gentlemen, this means that if we have the equation of the integral of this function, which is x squared plus x, okay, if you wanna know how to draw it, you just have to get the derivative, which is 2x plus 1, and then you plot it and you will know it. Okay, so we have a formula or an equation that calculates the area, but if you wanna exactly draw the line or the shape of the function, just to get the derivative of x squared plus x, and it will be 2x plus 1, and then you make the plot of the table, and then you will find this amazing result. So this is what we're talking about in this video. Now it is the time to give you the most practical example, is the insolation that comes from the sky or from the sun. How to make use of the integral concept and derivative or derivation in this practical example. So let's get started. So gentlemen, we have here the solar intensity from the sunrise to the sunset, and here is the hours of the day through the sunrise to the sunset, and here with the intensity. So why do we have to use the integral? The integral here, it means the energy in watt hour, okay, that we can get, because if you draw rectangles here and get the area of each one and add them, or get the summation, you will find yourself multiplying the time in hours by the intensity. It means watt hour. This is energy. So to know the energy that you can get from the sun at a specific moment or a specific day in the year, we use the integral. Okay, so for example, so we have here the extraterrestrial radiation incident on the horizontal surface, which should account for the cosine effect, which causes reduction of radiation by the cosine, the angle between the solar radiation and the surface normal. So we have here. So we got here some solar equations. We have here the energy of that we can get from the sun at that day, IOH. I'm talking about this specific quantity, the extraterrestrial radiation on horizontal surface. I need to calculate the energy of it. Okay, to calculate the energy of it, just let's see if we have a problem. No, just calculate it. So we got here 6396. 6396. It will be watt hour per square meter. If you have 1 square meter PV, you will receive IOH with this quantity. Of course, this is not what exactly happens. What exactly happens is that we depend on the I total, which means the I direct plus the I diffuse plus the I reflected. Okay, I'm just talking here about the integral and this simple quantity. But for the photovoltaic, we need to calculate the I total, not IOH, to exactly know the quantity of the solar radiation that will hit the surface of the photovoltaic. Then we will use this, for example, gentlemen, if you are familiar with MATLAB Simulink, you will be asked to put the irradiation in watt per square meter. So the irradiation is the I total that I'm talking about. You have to get the I diffuse and the I direct and the I reflected. This means the irradiation. So after getting the irradiation, you can also plot a curve like what we have just seen from sunrise to sunset. This means that you can get the integral, and this is the energy watt hour per square meter that your PV module will receive. But not all of this energy actually will be converted into electrical energy. You have to take into account the electrical part and the electrical efficiency. So now let's see how we're gonna use the integral. So this is the integral. Okay, so let's plot. So I've just plotted T solar to with IOH from sunrise to sunset at that day, specific day. We have here T sunset and T sunrise. I just solved the equations, so let's make the plot. So this is the plot. The area under this curve exactly equals to the energy here, 6396 watt hour per square meter. So now what if I wanna check, okay, what if I wanna get uh, the equation? So we're gonna use the curve fit, and this is parabola to be polynomial, and here too, and so this is the equation that we can use to get the integral and compare between the integration value or the integral value that we get from this equation to this value that we got from is here. Of course, this is the more accurate value because this is not the curve fit. Okay, so now let's calculate the integral from this equation. So now, gentlemen, just to finish this video, what we got is the area under the original curve from the integral law. What I predict is the curve fit that we got. We have here its equation, which is somehow this like or close to the original curve. So this equation, if we get the integral of it, we predict that we get the same area or a value close to the original area. In other words, we have here the curve fit, the integration from sunrise to sunset for the function that we got from the curve fit. It also, if you are using your hands at school or at the class, you will get this is the what we you will write by a pen to calculate the integral by the original calculator. So curve fit, it will match this curve fit. This is by hands and this will by east. Anyway, the two values should be close or the same, and the value will be very close to this original equation. So because here I do not need this, okay, let's see, we have 18 and 1 and of course 19. So let's see. So we have here the area from the curve fit 64 to 8, and we have here the energy, which is more accurate because this is the original curve, 6396. This is awesome because 6428 minus 6, okay, we divide 6396 by 6428. We got 6396 by 6428. So we'll get a percentage of error is 0.49%. This is pretty awesome. So, gentlemen, this concludes that we use the curve fit. Okay, we will get a very close value to the integral. Okay, from this equation we have here the curve fit. So to plot the relationship between the time through the day from sunrise to sunset, and to get the IOH value, you will need to get this equation. But to know the watt-hour value through the day, you have to integrate the this equation, which is the integration of these two. Okay, so thank you so much. This concludes the concept of the derivation and integral, and also we are lucky to talk about the limits. So thank you so much. This is the integral. The integral of the original curve is very close to the integral of this curve fit equation. Again, the integration is the area under the curve. If you wanna plot it, you have to know this equation. You have to get the derivative of this equation. Okay, so the derivative of this equation will give you the original equation, which can be plotted like this. Okay, so thank you so much for watching this video. If this helps you, we'll try to use the integral mathematics to solve our practical problems. So thank you so much. Wassalamu alaikum.